Last talk of the day, Simone Belli, brick by brick stabilizing the biaxial nematic phase.
Yeah, thank you very much. And sorry, first of all, can you hear me? Microphone works? Okay, great. Okay, before starting, let me first send the regards of my supervisor, René Van Rooij, who was invited here to give this talk. Unfortunately, he couldn't make it, so he sent me. And also thank the organizer for the invitation. Okay, let's see. It's actually, well, I should also thank the organizer for inviting me and to schedule my talk at the end of this day, because most of the topics I'm going to talk about have already been introduced by the other speakers very well. And with this, in this talk, we're going to try to see how difficult and, how we want to stabilize biaxial nematic phases. And before, and let me start by underlining a difference. I'm not going to introduce what liquid crystals are. I'm sure you all know very well what they are. But it's probably important to stress the difference between thermotropics and lyotropic liquid crystals, two different classes of liquid crystals. And the main difference between them is related to the fact that the building blocks of thermotropics are small organic molecules, typically, therefore, with the size maximum around the nanometer, whereas on the other hand, the building blocks of lyotropics are typically amphiphils, polymers, colloids, like in this talk, therefore with a much bigger size until the micrometer, and typically in a solvent. So these distinctions have pretty important consequences for what concerns the physics of the liquid crystals. And first of all, the control parameter for the liquid crystal transition is, in case of thermotropics, the temperature, as the name says, and for lyotropics, the density. This also has a pretty strong, let's say, effect on the type of transitions we are going to consider, because in thermotropics, you have the energy plays an important role in stabilizing the various liquid crystal phases. In lyotropics, typically, it's only the entropy. So the liquid crystal transitions are pretty much entropy driven, and this is precisely the case I'm going to consider now. So I'm sure that many of you are interested in the stability of biaxial nematic phases in thermotropics. I would say also because they can allow for basically evolution of the liquid crystal technology. This is not immediately the case for lyotropics, but in a way we know that there is a pretty strong connection between the two type of liquid crystals. So, well, maybe there can be an interesting lesson that we can learn from lyotropics and eventually to apply on thermotropics. So, let's start with uniaxial nematics, with nematic liquid crystal phases. What are they? They are, we can introduce them, we can define them as liquid crystal phases, as phases characterized by being homogeneous. Therefore, every point in space is equivalent to any other for what concerns the distribution of the particles, but anisotropics. And anisotropic because particles which have usually, well, which have a non-spherical shape tend to align, tend to assume a common alignment. And we know very well the case of rods, they tend to align their long axis. And we also know from the previous talks the case of plates, in which instead the particles tend to align the short axis. In both cases, the result is a phase, macroscopic phase, which is, bless you, which is, again, which is cylindrically symmetric in both cases. And the result is that if we consider the optical properties of the liquid crystal phases, of these two liquid crystal phases, they are both uniaxially they are both characterized by uniaxial birefringence, and therefore we call them uniaxial nematic. We distinguish between these two by saying that this is the prolate, and we indicate with this M+ sign, and oblate in this case. Now, one could wonder why to specify the difference between M+ and N- prolate and oblate. And it's important in order to understand the question Fraser asked himself in 1970, and already mentioned before, by the way. And the question he asked himself was the following: what happens if we consider particles which do not have this cylindrical symmetry like rods and plates. In other words, what happens if we consider bricks, what we call now board-like particles, as already mentioned by Professor Vanakaras before. Therefore, particles with 3 dimensions, length different by the width. I don't know if you can see the pointer, otherwise I'm going to use the analogic one. Is it visible? No? Okay. Well, anyway, length much bigger than the width, this one much bigger than the thickness. And why am I asking this? Because in principle we can expect both the phases to be stable and to be shown by these brick-like particles, board-like particles. Prolate if they align the long axis, and oblate if they tend to align the short axis. And in both cases, if you consider the symmetry of the phases, cylindrically symmetric in both cases, therefore uniaxial nematic. But what if it actually happens that the 2 conditions are met at the same time? Therefore, you have a phase which is homogeneous, therefore nematic, anisotropic, definitely, but not anymore characterized by cylindrical symmetry, therefore optical uniaxiality. And what you have is biaxial birefringence, and that's the reason why we call it biaxial nematic. So these are more or less the arguments suggested by Fraser, and well, actually people after him as well, in order to deduce the possible existence of this liquid crystal phase for this kind of board-like particles. Unfortunately, there is, as mentioned more than once before, a pretty, during the day, a pretty important problem that biaxial nematic phases are extremely difficult to obtain in practice. In other words, it's extremely difficult to design a system in which biaxial nematic phases can be observed as stable thermodynamic phases. So just to have an idea, and to repeat things already said before, this is a very short and incomplete history of biaxial nematics. We have in 1970 the prediction by Fraser, further theoretical work, the first biaxial nematic observed in micellar systems in 1980, and 2004 the first thermotropic biaxial nematic, and in 2009 a very nice experiment done in Utrecht and already discussed by Professor Vanakaras, and I'm gonna discuss widely about it. So I don't know, a colleague of mine noticed that between the prediction and the actual observation, well, this kind of, well, I don't consider it because some people were saying that this kind of observation was kind of controversial. But if you consider these like the first kind of clear observation of biaxial nematics, I mean, you have between the prediction and the observation like almost, how many, 35 years? So it's the order of magnitude of the Higgs boson, basically. So that's the difficulty in stabilizing biaxial nematics and in observing them. So it's a bit menacing, I'm sorry, but what's the main problem in stabilizing biaxial nematic phases for systems of board-like particles? The problems are smectics, as already observed before, and this is a theoretical phase diagram drawn at the beginning of the 90s by Taylor and Hertzfeld, in which you see that biaxial nematics in principle can be observed by tuning properly the dimension of the particles, but if you consider smectic phases, well, you don't really expect to observe them, but in a really tiny region of the space of parameters. So this is a bit sad if you want to observe biaxial nematic phases. But again, this should be compared with this recent experiment on a colloidal system, in which actually, performed by the way in Utrecht by Esther van den Peul and Gert-Jan Vroege and other people. And the important thing to notice in this case is that the biaxial nematic stability is huge. And it's extremely difficult to understand it in terms of the basically theory drawn and performed and analyzed previously. So this is the first question we want to address. How is that possible? Well, maybe it helps if we have a closer look to the details of the experiment. These are the board-like particles. Resolution is not great, but as you can see, dimensions of the order of 100 of nanometers, so it's a colloidal system. These are the average dimensions measured in the experiment, and with a certain degree of polydispersity. Polydispersity, as already discussed, it's the degree, basically the degree of dispersion in the dimension of the particles. High polydispersity means that the particles are very different in size between each other. 20-25% can seem pretty big, but actually for experimental, basically for systems synthesized in laboratories, not that high. So one could actually suggest that polydispersity could be the element stabilizing biaxial nematic phases. And by the way, this was suggested by the previous speaker 10 years ago precisely, that polydispersity could stabilize biaxial nematics. And how does it work? And very well, we can compare it with the phase diagram shown this morning by Professor Frankel. The fact that we know that, for example, if we consider rods, maybe a more familiar system, we know that in case all the rods have the same dimension, same length, the system undergoes a nematic-smectic transition. When you increase the polydispersity, therefore the difference in length between the rods, you reach a point in which the smectic phase disappears. And something that Professor Frankel didn't underline, but it's very important in this talk, is that as a consequence, the stability of the nematic phases increased, so very much. So what if this happens also in board-like particle systems? But the point is it just this? Is this enough to explain such a big biaxial nematic stability? And so what we want to do is study the phase behavior of board-like particles as a function of the polydispersity. But the point is how we're going to do it. This is not trivial for more than one reason. First of all, if we even consider only monodispersed board-like particles, the space of parameter is relatively high. We have 2 parameters to control, 2 aspect ratios. And of course, things become even more complicated if we consider polydispersity, because it means like considering different species with different dimensions. So therefore, a simulation approach to deal with the problem seems not really the easiest way to basically approach it. Therefore, that's why we're going to use theory to investigate this phase diagram. But still, even using the theory, the problem is that it's not easy to parameterize, to describe the interactions between board-like particles for arbitrary orientations in space. So now I'm going to show you like our simple, very simple theory we design in order to attack the problem. First of all, we work within the approach within the framework of density functional theory described this morning by Professor Evans. And rho of I alpha is the single particle density, is the density of particles belonging to species alpha with orientation I. So first of all, why am I saying orientation I? Because we introduce an approximation of the so-called Zwanzig model, a restricted orientation model, in which we actually impose the system to, well, the board-like particles not to take any possible orientation in space. If my hand is a board-like particle, it can't take any arbitrary orientation, but only 6. The 6 orientations in which the axes of the particles are aligned along the axis of a Cartesian reference frame. This simplifies a lot the calculation of the interactions. And with this kind of approximation, we can write the intrinsic free energy of this kind of density functional theory. Here we have the first term. Maybe if you're familiar with density functional theory, this is the ideal term. This is the interaction. We expand the excess free energy in the virial series. This is the excluded volume between 2 particles belonging to species alpha and alpha prime with orientations I and I prime. And there, of course, this kind of expansion is characterized by further higher order terms. And we want really to deal with the simple theories, so we just forget about them. This is kind of a strong approximation because it means that we cannot really expect quantitative, strong results to compare with the experiment. But our aim is to just describe qualitatively the phase diagram. And with this, we just follow the rules of density functional theory. We obtain the the equilibrium value of the single particle density by minimizing the free energy, and the symmetry of the single particle density tells us what's the phase of the system. In this case, by the way, I didn't mention it. This is important. In order to simplify the calculations, we assume the phases to be homogeneous. Therefore, we do not assume any dependence on the basically coordinate R. So we can only describe isotropic and nematic phases, but uniaxial and biaxial. And with this, before showing you all my phase diagrams, all the phase diagrams I calculated, let me first introduce this shape parameter. I told you before that describing biaxial particles, like board-like particles, it's not easy because we have two aspect ratios to describe the shape, let's say the more general shape of board-like particles. But in this work we consider, it's particularly useful and convenient to introduce this shape parameter already introduced by Professor Vanakaras, which is basically a combination, nothing but a combination of the aspect ratios characterizing the board-like particles. And I'm going to show you why in the next slide this kind of shape parameter is particularly useful. And to make you understand what's the meaning of this shape parameter, when this parameter takes values appreciably smaller than 0, we have plate-like particles, and the other way around. We have rod-like particles when it takes this sigma takes values much bigger than 0. So correspondingly, we expect the uniaxial oblate and prolate phases depending on the sign of this shape parameter. And just to compare with the experiment, the experimental average values of the aspect ratios of the particles are characterized by a value close to 0, but slightly bigger than 0. What consequences does this have? We see it immediately by considering the monodispersed case. So we don't introduce polydispersity yet. We just use our theory, and we see what it predicts for monodispersed board-like particles by changing this shape parameter. And this is why we introduced this parameter in this way, because when sigma is equal to 0, the phase diagram is characterized by a direct isotropic biaxial nematic transition, continuous transition, by the way. Whereas for values different than 0, you have a very slightly first order from this, from my calculations at least, to prolate or oblate uniaxial phases, therefore alignment along only the long or the short axis. And well, at higher packing fraction, we use the bifurcation analysis to actually set the limit of stability of inhomogeneous phases. So in a way, this tells us, at which packing fraction we can observe nematic phases, beyond which we expect instead the nasty smectic or columnar or crystal phases we don't want. And let's compare this phase diagram with the experimental numbers for the average dimensions. And if we, for example, fix the two, basically the values of length of width and width, the two basically average values of the dimensions of the particles, we see that we expect to observe a biaxial nematic phase only if the third dimension has this kind of this value between 26 and 28 nanometers. This means a control on the dimensions of the particles at the level of the nanometer, which is very difficult to achieve, not considering polydispersity. So that's that's basically the reason why it's difficult to interpret the experiment only in terms of monodispersed particles. So polydispersity, how can we analyze it? Well, the problem is complex because in principle polydispersity means many different species. So we use just a simple model to analyze the system of and size asymmetry, the effect of size asymmetry, and it's a binary mixture. So only two species, and basically they have exactly the same shape, but we multiply the values of the dimensions of the first species with the parameter 1 plus s, and on the other hand 1 minus s for the second species, so that s is a parameter we call size asymmetry in such a way that s, well, when s equal to 0, the two species are the same dimensions. We increase s, one becomes bigger, the other becomes smaller. So the question is, how does the binary mixture behave as a function of this size asymmetry? Let's see it. This is, oh yeah, by the way, this is the approximation I introduced. Basically, 2 is a good approximation for infinity in this case, hopefully at least. And this is the phase diagram. We have the Packian fraction on the y-axis. X-axis is basically the mole fraction of one species, in this case the big particles. And here, this bottom axis represents the size asymmetry. S equal to 0, we have the two species are the same, so basically there is no dependence, of course, on the mole fraction. What happens when we increase the size asymmetry? Green is, yeah, maybe the colors are not very clear, but green is biaxial nematic phase, blue is the oblate phase, and red is the prolate uniaxial phase. So let's see more in detail. S equal to 0, size asymmetry is 0, the two particles are the same. If we introduce the average values of the for the dimensions of the particles from the experiment, we observe just a direct isotropic uniaxial prolate nematic phase, therefore no biaxial nematic phase, as expected from the theory. When we increase the size asymmetry, we have, first of all, the decreased stability of smectic phases, as suggested by the work by Professor Vanakaras. But furthermore, there is another effect, a decreased stability of n plus phases. And if we go even further, what you observe is like a qualitative change of the phase diagram with the appearance of these Landau critical points, which basically appear as a result of the competition between n plus and n minus ordering.
Sorry, maybe I missed it. The x1 here is the mole fraction?
Of the big particles.
Okay, thanks.
Yeah, precisely. And so you have like this kind of competition between n plus and minus. You have the appearance of these Landau critical points, and as a consequence, you have this opening of pretty wide biaxial nematic stability. So this is very interesting. And we can compare this with an even more realistic model for polydispersity, not 2 as an approximation for infinity, but 20 as an approximation for infinity. So 20 species whose dimensions are distributed according to Gaussian distributions as a function of the basically standard deviation of this distribution, which is the polydispersity. And again, what do we observe? 0 polydispersity, particles all the same. We do not observe any biaxial nematic phase. We increase the polydispersity, again, we observe this competition between prolate and oblate behavior. And as a consequence, you have the opening up of this pretty wide biaxial nematic stability. Let's compare it with the experimental values for the polydispersity. And as you can see, well, I mean, our data are kind of compatible with a pretty wide biaxial nematic stability. And by the way, no, or almost no, uniaxial nematic stability. So, after this, we can draw the first conclusions from these analyses, this work, that indeed size asymmetry stabilizes or can stabilize indeed biaxial nematic phases, at least in colloidal systems of board-like particles. And in this sense, we can explain the disagreement between theory and experiment. And furthermore, the phenomenon, this kind of phenomenon is associated, again, with this competition between prolate and oblate uniaxial nematic behavior, which is still not really understood. So the next point to be addressed is what is actually the reason for this competition. And we address this point by changing our perspective slightly. And let's go back to the simplified binary mixture of big and small board-like particles. If you observe this kind of system, maybe it can look like a system which has been widely studied in the past, and I'm sure many of you did it. And in a way, this is kind of similar to binary mixtures of big and small spheres. And by the way, for this kind of suggestion, I have to thank Randall Kamian, who actually pointed out this kind of analogy. And what happens when you have big and small spheres? Well, you can describe the behavior of this binary mixture in terms of a depletion interaction. That is, if you assume that there are only, let's say, hard interactions between between big and small particles, hard interaction. In that case, you have that there is a region around the big particles called depletion region, within which basically the center of mass of the small particles cannot go because of the hard repulsion. And when you have like the superposition of the depletion regions between two of these big particles, you have an effective attraction due to this uncompensated osmotic pressure, basically on this side and on this side. And if you further assume that there is no depletant-depletant interactions, that the depletants behave with themselves like ideal particles, well, in that case, you can actually compute explicitly this interaction, this attractive depletion attraction, and it's given by the density of the depletant, density of the small red particles, well, multiplied by a geometric factor, which tells you basically the volume of this overlap region as a function of the distance between the two big particles. So, all this kind of analysis to say, or this kind of description to say what? That if actually that's the case, and binary mixtures of big and small board-like particles behave like big and small spheres, maybe we can observe similar behavior if we, instead of considering this binary mixture, we consider a system of attractive board-like particles. And well, basically this kind of yellow area region is to underline the fact that between the board-like particles there isn't just hardcore repulsion between, well, basically non-overlap conditions between their volumes, but also an attraction which is proportional to the density of this depletant. And we can actually analyze the phase diagram of board-like particles, these attractive board-like particles, as a function of the depletant density. Therefore, for depletant density equal to 0, there is only repulsion between the board-like particles. We increase the depletant, we have an attraction which is stronger and stronger. And we analyze this phase diagram, showing again isotropic and all the uniaxial phases and the biaxial nematic as a function of the shape parameter of the board-like particles, how much the board-like particles are rod or plate-like. So we start from the from a negative value of the shape parameter. Therefore, we expect at 0 depletant density only a stable uniaxial oblate phase. And actually, for every other depletant, for even increased depletant density, we still observe this kind of simple oblate uniaxial phase. But what happens when we make the particles more rod-like, when we increase the value of this shape parameter? We can see it. So again, we have, by the way, we have values of the shape parameter bigger than 0. Therefore, we have like rod-like behavior and stable, basically an isotropic N plus transition. N plus is again the uniaxial prolate phase. But what we observe is that when the depletant density is high enough, you have actually a stable oblate uniaxial phase, and again, as a consequence, a region of stable biaxial nematic states. So, well, this is also shown in more detail, but first of all, how can we interpret this effect, the appearance of this Landau critical point and the stability of oblate uniaxial nematic phases at high attraction between the particles? Well, if we interpret the phenomenon only in terms of attractive board-like particles, I think it's fairly easy to understand. That is, when the density of this, well, when basically there is no attraction, what pushes the transition is just the entropy. And therefore, if the shape of the particles favors prolate ordering, like rod-like ordering, that's the case, and your particles will align along the long axis. But when the attraction between the particles becomes stronger, it's energetically favored to have stable phases in which actually there is a higher, if you want, shared basically surface between well, due to the configuration of the particles. So therefore, you know, they tend to prefer oblate ordering. And again, as a competition of these two effects, you have basically the appearance of this Landau critical point. And then again, we can change the perspective and go back to the binary mixture, and we can say, okay, that's probably the same thing that happens for the binary mixture, with the only difference that in this case, when the concentration, when the mole fraction of small particles is high enough, oblate ordering gives basically higher entropy, higher available volume for the small particles to to occupy in the space. So it looks like the two systems, the two models are kind of related in terms of phase behavior, and we can finally compare it with these two phase diagrams, which are fairly different in terms of the basically model. In the first case, we have size of polydispersity. In the second case, we have instead monodispersed particles, attractive though, where the attraction is determined by the non-adsorbing depletant. And well, I think they show many similarities, and I don't know, I think it's reasonable to interpret the two phenomena according to this common interpretation. And with this, we can draw the second part of conclusions. First of all, that it looks like that size asymmetry indeed favors oblate ordering. And this is a consequence of the increased positional entropy of the small particles with respect to the big ones. And by the way, this is a result obtained for free, that the addition of a non-adsorbing depletant and therefore the introduction of depletion interaction can be a way to control the phase behavior of board-like particles. And I think that there are people working on these in terms experimentally in Utrecht. So all this discussion to show you that actually bricks can be useful to stabilize this biaxial nematic phase. This is in a way probably the kind of an optimistic way to see the long process of stabilizing biaxial nematics. Maybe more realistically, we have this as a case. But with this, let me thank you very much for your attention.
I'm a little confused that in the phase diagrams for the bidisperse or polydisperse systems, I didn't see regions of two-phase coexistence. Did I miss that, or?
Yeah, no, that's a very good point, and that's a point I didn't address. And yeah, I agree. This is kind of this is the phase diagram. I agree. This is something surprising in a way. But according to our free energy calculations, there shouldn't be much demixing. And the reason for this is probably associated to the fact that board-like particles by themselves, when they have like a shape characterized by a space, by a, I'm going to show you the monodispersed phase diagram now. when you have particles characterized by a shape parameter close to 0, according to our theory at least, well, I think it's probably the case also for freely rotating board-like particles, basically the transition to the nematic is almost continuous. And apparently this has an effect when you consider polydisperse, the binary mixer case. Just a second. Well, apparently this seems to be the case also for binary mixture, independently of the size of symmetry, since you expect like a very weakly first order transition at mode fraction 1 and 0, and at the same time you have this, due to the appearance of these Landau critical points, in this case you have also continuous transitions, and apparently that's the case also in the regimes in between. So this is in a way our interpretation to, well, maybe not really motivate the absence of the mixing, but try to interpret it.
Are you suggesting that the same thing applies for the transition into the smectic phase or the more ordered phase? Are you expecting not to see very much fractionation between the two phases?
No, I didn't say that. Actually, I don't know. I would probably expect kind of strong fractionation if you consider smectic phases. Yeah, but this analysis doesn't really involve the smectic.
So the bifurcation analysis wouldn't pick that out?
Well, I'm actually not sure how easy it is to calculate, well, explicitly calculate bifurcation, fractionation only by a bifurcation analysis. I think you would need to explicitly calculate the free energy of the smectic phase, and that's kind of more complicated. Not impossible, maybe, but...
Simone, the depletion picture is very nice. In the spherical case, as you know, if you have non-interacting depleted, then for size ratios, the ratio of the size of the big ones to the small ones, the mapping to a one-component system becomes exact when that size ratio is less than 0.154. Do you have analogous results in your case? Very small. Can you prove anything?
No. Unfortunately not, at least not within
Are you sure you can't?
Can you?
No.
You can try, of course, Professor Evans. I actually invite you. But I would say that in this particular model with cuboids with pretty sharp edges, that's not the case. So in principle, that's another approximation we introduced. We only consider two-body effective depletion interactions. In principle, you should consider higher body interaction terms, and we didn't. On the other hand, probably if one uses particles with a maybe more physically reasonable shape, like that considered by Professor Vanakaras of the spheroplatelets, well, maybe in that case, maybe one can find a minimum value of the depletion so that you can completely neglect higher order interaction terms.
I would think of a depletion interaction, at least to a lowest order, as being at least a three-body interaction. In this case, between two big bodies and a little one. But you only have two-body interactions in on-saga theory. Do you think the two theories really are connected?
Yes. Who answered for me? No, but in any case, yeah, well, definitely it's three-body interaction in that, well, I'm talking about two-body effective interactions. So in a way you have if we consider just the spheres, for example, you have the effective interactions between two big spheres because of the presence of the small spheres. Yeah. But it's still like a two-body effective interactions, although of course like all the small depletants, come into play and they actually determine the effective attraction. So, well, in that sense, is a two-body interaction.
No, I see that. I thought you were saying, but maybe I misunderstood, that your on-saga theory contained depletion effects somehow.
No. Well, no. Of course, no. That's not the case. We introduced we actually introduced this depletion attraction by modifying the excluded volume between the particles in terms of, let's say, effective excluded volumes, which are probably lowered in value due to the presence of the attraction, but it's still two body.
I misunderstood, sorry.
Yeah.
So could you explain why the isotropic to nematic transition never changes in packing fraction when the mole fraction of the larger particles change? I mean, those lines, those horizontal lines are a bit peculiar.
Yeah, well, I mean, I can explain you easily why, let's say, the isotropic nematic transition takes the same values here and here, because, well, in the basically on the y-axis you have the packing fraction. So basically, if you draw the phase diagram of the monodispersed system, it doesn't really depend on the size of your particle, but only on the aspect ratios if you plot it against the packing fraction. So you see my point.
Sure.
So, well, I mean, if you instead are asking me why it stays, pretty much constant and it doesn't change, at higher or lower values, well, I cannot really answer easily. I can say just that this is the output of the theory. But it's interesting, and I agree.
In your phase diagram, the transition from isotropic to biaxial always happens at this triple point. I wonder whether this is the consequence, kind of fundamental property, or it is just a consequence of having chosen just a finite number of orientations in your theory.
No, I wouldn't say it's a consequence of the discrete orientations of the theory. On the other hand, the generality of this picture, I think it's kind of difficult to establish only in terms of this kind of density functional theory approach. I'm sure that there are in the audience people who studied the problem in terms of Landau-Desjardins theory, and probably they can discuss the full generality in this case of the basically isotropic biaxial nematic direct transition in only one point. But from this density functional theory, it's pretty difficult to draw general conclusions. But I wouldn't say in any case that it's a consequence of the restricted orientations.
Any more? Well, thank you for leaving so much time for questions.